So the agenda, and I'll try to get through this fast because I tend to not, 40 minutes is a challenge for me. So let's talk a little bit about facets, and especially why solar faceting particularly rocks. As you know, I'm senior, so I've been doing this for 15 years. Started working with Verity back in '01. So I've seen them all. And then we're going to talk about text and language, a subject near and dear to my heart. Any of you who follow any of my blogs would know this. And we always call it in the search business unstructured text, but I hardly think it's unstructured. Certainly linguists would clearly disagree with that. And we're going to then show, we're going to talk about the boring stuff, hopefully pretty quickly, and then some interesting things that I've been doing lately. I've blogged about a lot of this stuff, so some of you may already know what's coming along. But basically the idea is to use facets as context mining engines. And that is actually the takeaway message that I'm going to leave you with. I gave a webinar recently where the word context was like right there. There's the biggest word because that's a really important thing in search and something we need to get right. So back to the start point, facets are metadata. And this is actually a definition that was taken from the web, like most people do research, so do I. Googled it and then got this definition, a particular aspect or feature of something. So metadata is basically, as we know, data about data. And there are various types of words that we use to describe metadata: attributes, aspects, descriptions, features, etc. And a lot of those work their way formally into like properties fields, things like that. So facets are metadata. But what I want to talk about more interestingly is metadata semantics. So everything, every concept has meta information about that thing. And some of this tell us the W questions like what, where, when, why. Usually not why. That's a hard question. And then, more mundane things like name, size, shape, etc. And different objects might have different types of facets, like who manufactured it, the number of outlets it has, etc. Address, phone number for people, hand size. Like actually, there's some political stuff in there. I'll just gloss over that. Couldn't resist. Believes in climate change. Hopefully, everyone does now. Metadata dependencies. Some metadata fields depend on what the thing is, and this is actually an important problem in e-commerce. We know that people have different attributes than toaster ovens. I actually recently blogged about the Google toaster a while back, so I'm going to have to move forward because I'm already getting a little behind myself. It's a little history. This is what the different search engines called facets. I was working with Verity K2 before they became Autonomy, before they became HP, and they called them parametric search. And that was an experimental feature. Fast called them navigators. When Microsoft bought Fast, last time I was in Vegas was actually for an MS Fast show where they were saying how SharePoint Fast is going to be so great. There are a lot of skeptics in the audience, including me, who were proven right. Well, MS Fast, Microsoft changed the word to refiners. Endeca calls them dimensions. Solar calls, of course, facets. Google and also Autonomy, basically their response is facets. We don't need no stinking facets. And actually, most of you will probably get the movie reference. But the interesting thing, I was at the party last night, and we all needed badges. But I ran into our CEO, Will, and a CFO, Reed, and they were with was introduced to me as a board member, and he didn't have a badge. I didn't get his name. So actually, the Lucidworks honchos could clearly say, we don't need no stinking badges. The rest of us had to bring our badges. So traditional use of facets, we all know this. Faceted navigation, that's actually a fast term. Microsoft changed to refinement. We call that drill down. It basically allows the initial query to be ambiguous without requiring the user to actually refine it, because then they can click on stuff. And it neatly handled. Before that, if your query didn't work, you had to rethink your query and put it back in. You're constantly getting no results found, and you keep changing it. And it's a real pain in the neck. Well, facets actually make it possible for the no results found to be never happens, because they're built from the result set. Downsides of facets, I think, are important to realize. And Endeca, actually one of my buddies at Endeca, actually bragged on this. That you basically tune for favor recall over precision, because then we make sure we get everything, because you can't click on, you have to click on something. But the need for this forces us to favor recall, so we basically get crappy search and then we drill in. So that's a downside. If you don't want to do that, then you want better search. And actually, that's really important because users do. Facet noise is an interesting one. If you have poor precision, the facet engine sees everything. So that's why in facets you sometimes get these weird outliers. My favorite example was searching for mattress pads and I saw baby strollers because they have brake pads, or searching for brake pads and got baby strollers, or furniture because they're looking for mattress pads, things like that. And those show up in the facets, even if your relevance is pretty good and you're showing all the best stuff at the top. So that's one thing. A more interesting one is gaining maturity rapidly, and we've seen this a lot, is visualization. We already know this from the classic search UI, that facets have a basically global context, I call it, of what the result set is about. Then we use these for dashboards like search-driven BI, eye candy, like all this great pie charts and bar charts and histograms are all powered by facets. And now Solar has enhanced faceting with analytics capabilities, which allow you to do more useful things than just counts. So we can get mean standard deviation and even more complex stuff like, like skewness and things. And a lot similar to what used to be done in the old days with the database OLAP cubes, but OLAP cubes, of course, are very static. Once the developer creates it, then that's what you get. The great thing about search is that these things can be search-driven, so that the cube can change with the query. And Index actually exploited that a lot when they did their same thing. They used to talk about it, but one of the main reasons why Solar is actually a better engine to do this is that Solar facets are dynamic, not static, meaning they're computed at query time. In other search engines like the ones I've worked with, and my buddy Mark Bennett also knows this, he's worked with all of them too, is that in Solar, the facet values are in these old engines like Verity Facet and Deca, the facet values are always computed at index time, which means they're static at query time. They're not going to change. Lucene, when Cutting originally created it and people enhanced it, didn't have faceting. And Solar added the faceting basically on the fly at the query time. And it did this after Lucene was basically a pretty baked product. And this is the main hurdle, of course, is making it fast. Because every time you have something in index time, the query time that's slow, you want to do it in index time so queries won't be slow. And thanks to Yannick Seeley, who basically did the original stuff on this for Solar, this is true. And although it seemed to be what we call a bolt-on because it was added after, in hindsight, this is a very lucky evolutionary path. And I was actually talking to Yannick about this and kind of verified most of what's on this slide. Because once you do this at query time, there are serious advantages, especially flexibility. In Solar, also, besides just what you indexed and how you designed your index when you're designing it, you can facet on just about anything, even things that you didn't think about when you were designing the index. You can build function queries, we'll talk about that, which are extensible with value source implementations, all really good. And as we'll see, this is stuff, and that's what's driving all this innovation that you're seeing on the dashboards. And this is a very brief survey of faceting methods. They're basic, facet on metadata fields. You can facet on anything, like I said, so you can actually facet on tokenized fields too, but why would you want to do it? And that's actually a sort of like a straw man. Remember that question, because I'm going to violate that rule later in the talk. And the basically two methods that we started with, the enum method, which is basically filtered queries, and the FC method, FC stands for field cache. Now we use doc values. So they're basically, and these are the types of query things you can do with it. It's not exhaustive, not intended to be, but you can call it queries for ranges, which are good for type head and lots of other things. Facet range queries, function queries, pivot facets. Basically anything, any result set that has, that you can count the items in it, you can facet on. And JSON facets is a new innovation that Yannick has provided, and actually gave a really neat talk today. It was partly about that and partly about streaming but I told him he needs to blog on it because JSON facets are actually pretty powerful. And one of the things about facets is there's performance tuning gotchas. Like if you're going to use the enum method, make sure your filter cache is big enough for the number of items that you have, or else it can be very, very, very slow, okay? So little things like that. I could talk about this for a long time, but nah, read the wikis. That's not what we're here for. I want to talk about this kind of stuff. So language semantics. What do I mean by that? Well, language is composed of things like nouns, verbs, adjectives, and so forth. So there's some metadata of a fantasy car, right? What type of car is it? It's a Lamborghini. What's its name? How's it made in Italy? How much does it cost? Much more than I can afford. How fast does it go? Really fast. And how much does it cost? Well, if you have to ask that, then why am I giving you a test drive, right? So my search philosophy is that humans use language to search because that's how we think about things. Whereas search engines don't really understand language too well. We're working a lot, and there's a lot of talks that are very exciting. We're doing a better job, but really that's the key thing. If search engines could do a better job of understanding language, they could better help us find what we're looking for. And a search index schema is actually describe a machine-oriented data-centric view of things. That's very important. Data-centric versus a language-centric. So search engines are data-centric. They work on metadata and stuff. And when we have descriptive text, we call it text. Because to a search engineer, that's what it is. It's just a bag of tokens, and we try to find stuff. So we really want to look at from a search engine perspective, but descriptive text is really not unstructured to us, and we assume that the computer knows that too, but it really doesn't, so we have to figure out how to make sure it does. So well, I'm going to talk about some interesting, basically yin-yang types of things. So we have a metadata, which is the search engine index. It's a data-centric view of things, and we have text, which is what we like to read information. We don't like to read like spreadsheets. We like to read descriptions. You know, this is a really fast car, costs a lot of money, it's really beautiful, whatever. You're going to love it if you can afford it. But what I want to show you is that metadata terms are embedded in language, so you can actually go both ways. You can compose descriptive text about a thing from its attributes or properties. You're creating linguistic expressions from metadata, and you can deduce attributes or properties of a thing from a descriptive text. You can compute metadata linguistic analysis. A lot of people doing this, we call it classification or tagging. But what I want to show you today is you can actually use facets to do both of those things, which is kind of interesting. So the search problem is to match terms in the query with things in the index. And if you know more about, and it's another theme here, if you know what the word means in a query, there's some powerful things you can do that you can't do if you don't know what it means. And facet metadata actually has knowledge about what things mean because we've tagged it with field names, which we can infer. So if the field name is color and the value is red, we know now that the token RED is a color because it's a value of the red field in our metadata. So that's a core concept that we're going to see again. So this is where I'm going to stop for basically the elevator slide. This is the take-home slide. So facets are context discovery tools. The facets that you see on a UI are basically the global meta-informational context about the results that you're looking at. So lemma 1 says that similar things occur in similar contexts. Okay, that's usually where we start with a Euclidean proof, something that everybody can agree on. Lemma 2 says that facets are context exploration tools, which I'll try to prove to you. So if 1 and 2 are true, then the assertion is that facets can be used to find similar things. Okay, follows? So I'm going to show you a couple of ways that I've been exploiting the facet metadata. And as I said, they provide a sort of global metadata context. Some of you may be aware of some work I've been doing called Coretta filtering, where I'm basically turning facet data inside out, and I'm using that knowledge map, which is the structured index, to figure out what words mean, and then applying that to the query to figure out what parts of the query mean what. So actually, I'm going to cover that. But then you can go further, and you can start using facets to build a contextual type head, because we want to suggest things to users to click on that we know we can solve, right? So that's kind of a no-brainer. And I'm going to show how I can use pivot facets, which is another interesting facet invented by my friend Eric Hatcher, but he called them tree facets at the time, he told me. We can use pivot facets to construct what I call these phrases from patterns. And the phrases will be things that are actually in the index, so they'll work well for type ahead because you know they're going to hit on something. They're not just random phrases the one thinks up. They're actually based on the data in the collection. And then I'm going to show you how we can extract related information using facets at index time, basically to, in type ahead, to do two interesting things: security trimming, which I won't talk a lot about, and dynamic boosting, which is a context thing. I'll talk about that. And then, if I'm not out of time by then, I'm going to look at facets for text analytics to generate better facets. And I've actually done some pretty interesting work. I blogged on this, and the second blog is supposed to come out soon. But basically, we can use facets to find similar terms to other terms in unstructured text. Whoa, that's pretty cool, because I can actually isolate what are keywords, which is an important concept, but it's hard to define what a keyword is. And I'll show you that I think these are pretty clearly keywords, and then I can use that to actually find documents that have the same context. So that's at the end. Hopefully I get there. So I'm not going to try to make this like a speed talk yesterday, but I'm going to have to move forward. So here's some examples of some metadata phrases. I've been working at recently at an e-commerce, they're basically a retailer of home products. So that's where a lot of this comes from. And I actually learned a lot on that job. And so, you know, we want to separate what from what about, because when people are searching for stuff on e-commerce sites, their user intent is pretty clear. They're going to say, microwave-safe dishes, or I want a compact microwave oven, or microwave, or coffee filter, coffee tables. These are all types of queries that people will put in. But you see, microwave occurs in different contexts. Either it's an adjective, or it's a noun, or it's used by itself implying another noun phrase, microwave oven. Coffee filter is a noun phrase, which means a filter, but coffee is a noun, which means the beverage that you use the filter to create. Whereas coffee can also be a table, it can be a color, it can be a flavor. And I was actually explaining this to somebody yesterday, and I'll show you the kicker later, but with the noun phrases, but basically, oh yeah, milk chocolate is chocolate, but chocolate milk is milk. But they're the same two words, but they're just flipped. And there's actually a semantic logic that everyone understands, but once you code it, you can actually do some interesting things. So query auto filtering, getting back to that, basically uses the field values that are in the collection to build yet another inverts the uninverted map yet again. It's another type, as you know, the actual search index is a kind of inverted map. It maps tokens to documents. This one is going to map values, token value to fields. So, and then it uses that map at query time. It uses a really fast thing called a synonym map, which is a Lucene thing, and it's a finite state machine, so it's really quick. But it uses this map to parse the query to find the terms in the query that are related to specific fields. So if I type in red sofa, it knows that red is a color and that sofa is a product type. So it can apply those appropriately to the metadata fields. And what it will select the log is contiguous phase that it finds. So if you have coffee and coffee filter in the lexicon, which is actually the Solar collection in this case, it will know it's a coffee filter because that's a longer phrase than coffee. And you can either use it to construct a Solar filter query to actually get very good precision. If you know exactly what the user is looking for, just go for it. That's the idea. Or you can use it as a boost query. And I actually did some work recently on a Fusion version of this where I've actually split those out so you can do both and you can actually control them better than the original Solar query component. So Coretta Fielding is a way of knowledge mining because it's exploiting the field value relationships that are already in the collection, and basically it's extracting that knowledge, and then it's using that to parse the query. So it knows that red is a color, because I already talked about this, so I'm going to skip through most of this. And it short circuits the search then drill in paradigm. You just have to search. So if it knows you're searching for coffee filter, it's not going to find a bunch of other stuff. It's just say, oh, you want coffee filters? I'll just show you coffee filters. And for e-commerce, especially mobile, this is huge because you don't really want to have to do a lot of faceting on your iPhone. You know, you don't want to slow down that one. So actually, that's, I think, pretty important. But as the telemarketers say, wait, there's more, right? Because the knowledge about what terms mean and the properties of the term field, whether it's single valued or multi-valued, turn out to provide other opportunities that we can exploit. So basically the key theme is here, once you know what a term means and where it comes from, you can do things that you can't do otherwise. And one of those things is language logic, which I discovered in this, because humans, especially in English, I don't know about other languages, but in English, natural language use of and or is not strictly mathematical Boolean. In some contexts, it can actually mean, they can actually be synonyms, and in other contexts, they're antonyms. So, for example, in an e-commerce site, if someone says, show me green or blue shirts, that's basically the same thing as saying, show me green and blue shirts. What they mean is they want to see both colors. So and or, in this case, are actually synonyms because they really mean both. They really mean union. Whereas if they say, show me fast and inexpensive cars, which may be mutually exclusive, but the attributes field is multi-valued, so you can actually do that and see if there are any fast cars that are also inexpensive. And this whole logic depends on the field cardinality. If something is single valued, meaning that all the values are mutually exclusive, then you can't really do and humans understand this intuitively. They know that or and in that context really means both. I want to see each of them. Whereas if it's multi-valued, yeah, then you want the intersection of the things you're interested in. I want inexpensive cars that are fuel efficient and can seat 4 or 6 or 8, whatever. Search engines really don't get this, but the query autofilter can actually figure this out because it knows the cardinality of the fields that it's mapped to. So that's an interesting one. Here's another one, which I've actually improved a great bit. So once you know what the individual terms or phrases mean, you can actually exploit this to create templates for popular queries. And the demo is Who's in the Who, which is all stop words, based on a music ontology that I developed this stuff for. And I'm actually going to show you how we can actually answer that question. Any search engine type in those are all stop words, and it's not really going to work too well if it's just using classical relevance. But if I tell it that basically I have this query template where I'm looking for patterns, and the patterns are a field and then maybe some terms. So the query pattern is all the different variations of who's in, like who's in, was in, were in, members of, and there are others. And then a query autofilter field called hasPerformer, which is basically a template. So when the query autofilter sees it, says, okay, do I see the term who's in and the who? Actually, I've already mapped that to a hasPerformer because I know that's a rock band. So I'll say, okay, that template matches. Now I'm going to substitute it into this query template to say member of group is hasPerformer. Another one would be like the songs Beatles covered. So song and songs are terms, and then hasPerformer, and then covered. And a cover is something where neither John, Paul, or George or Ringo were actually the author of the song, but they performed it. So you can actually use this to find all the songs the Beatles performed or recorded that they didn't write. And there's actually some logic under the covers which builds the ontology, the flat map, correctly. And if you do this, and you put it into my demo, which I would have gone live with. I tried it in Austin, but the demo gods hurt me, and somebody said in Vegas you don't want to piss them off. So basically it works. Roger, the 4 guys, right? And it's a all stop words query. Cool, huh? So yeah, I'm running late, so I need to speed it up. want to get to the good stuff. So the next thing is, if I have patterns to basically translate queries, I can also create patterns to create queries using pivot facets. And so here's an example going the other way. If I set these patterns up, has performer, then recording type, and throw pivot facets at a collection and collect all of the paths, I get things out of my music like Beatles songs, Led Zeppelin songs, Billy Joel songs, etc. Or I can have genre musician type, get these, recording, etc., and then I can throw those into a type ahead solution, and I know already that I can solve those questions and get the right answer, which is kind of nice. So I'm going to build a suggester that has not only this stuff, but also has what I call dynamic context. Here's another example of using facets. So facets can be used to find similar things. So the example here is John Lennon and Paul McCartney. Obviously, they share many attributes, activities, group memberships, etc. They're very closely related entities. And in fact, in my music ontology, because I have almost all the Beatles songs that co-wrote most of them, they're the two most related entities there are in that particular database. So in search agendas is another thing. Users tend to have some goal when they're searching, like find stuff out about the Beatles. And the agendas can change in a session, but it's likely that the queries issued within a short period of time have the same goal. So we can actually use facet meta information to associate similar things or concepts within a search session, and I'll show you how that works. Basically, this is a slow one. Here's the code, and this is also a Fusion thing now. It's a connector. Basically, you have a pivot facet which collects all these, generates all these queries, and then you execute the query against the content collection, and you ask it for facets, related information. You put that back into the suggester collection as sort of meta information about the type ahead, and then you build an app which basically uses that information for boosting. And two of the use cases were security trimming. When you type ahead, you don't want to suggest a suggestion that the user can't get any data on because they have no privileges. But the more interesting one is the dynamic boosting. So again, I'm running a little slow here, so I want to make sure I get through this. And I've blogged on this, so if I'm going too fast, you can always read that. It's my Jimi Hendrix blog. I call it that because I use Jimi Hendrix graphic. So basically with the suggester, the dynamic context, this is a client-side thing. It gets the type head thing, like Paul McCartney, and then it brings back all of Paul McCartney's meta information context and stores that. So if a query is used to search, it basically stores that in a cache, so only the most recent meta informational context is retrieved. But when submitting the next query, it adds that cached information back into the query as a boost. And so what happens in this, if you type J with a naive thing, you haven't done anything yet, this is what you get back. But if I had just searched for Paul McCartney, when I type J, I see John Lennon. Now, there's one in there that I don't understand, James P. Johnson. I don't know where that snuck in. You know, nothing's perfect. But other than that, it's getting pretty good stuff. John Lennon's songs, Cone's Covered, and then Hey Jude, which is, of course, the Beatles song. So this is a way, and the reason this works is because Paul McCartney and John Lennon are similar entities, so they share a lot of their meta informational context, which I've extracted using facets. So, and this is what I just said. Here's Paul McCartney's meta informational context. Member of group Beatles, Wings. Of course, that old joke about the kid who said, oh, Paul McCartney was in a group before Wings. You know, that was actually a joke that's out 20 years ago, so that just shows how old I am. And then here's the dynamic boost query, and you can see that it's John Lennon is in there along with the other Beatle guys who John Lennon is associated with too, like Ringo and George, member of group Beatles. There's some interesting stuff in there that you actually come out like Sonny Bono. Yeah, and Michael Jackson, actually Paul McCartney co-wrote some songs with those guys. So I don't remember what this, I know Michael Jackson was a co-author of a song, but I'm not sure about Sonny. And any questions, why isn't Cher there too? I don't know. Anyway, so that's one example of using meta-informational context to find similar things to boost things that people are interested in because they're searching about Beatles stuff, right? And it works across a lot of different things. If you just have context information in your type ahead and you throw it back as a boost, this will work, no matter how you get that other context. In my case, I basically engineered it to have it because I have this ontology which I rolled into a collection, so I have all the relationships and all that mapped out nicely. But what happens if you don't have that crisp metadata? Can you still use this technique? Well, that's where we need to actually pull metadata from text. This is more real world. One case is working at this product company that I've been working with, extracting product type and product attribute metadata from short product descriptions. And that's actually a fairly simple case I'll talk about a little bit. And then large text documents, this is actually pretty killer. I want to extract keywords and categories, which is a lot of what this machine learning stuff does. But an interesting property of facets when directed towards unstructured text, and this is where I'm going to break the rules of faceting on tokenized stuff, is if we take facet ratios of the positive and negative queries, we get almost immediately these really good clusters of related terms, kind of like Word2Vec, but with far fewer documents. And then we can cluster on those documents to give categories, and I'll show you a little example of that at the end. So it's simple keyword analysis. Basically, take the information, we run it through the Spark analyzer that has the Lucene analyzer in the middle with this auto-phrasing component, which I'll talk about in a second, and it has this new thing called extensions, which I'll talk about, and some special sauce ingredients. We want semantically pure lexicons, things that are about things or attributes or dimensions, but not mixed. We're going to use auto-phrasing, which is a previous solution I came up with, and I'll talk a little bit about that. And we want to actually remove stop phrases like Mr. Coffee is not coffee, it's a brand of coffee maker. And then we want to use these things I call expansions and relations to basically extend the recall and precision. I'll talk about a little bit that, and then there's some tricks to deal with things like leather case for iPhone. We're really looking for a leather case, not an iPhone, and a digital camera with a lens. We're looking for a camera, not a lens. But I want to talk a little about expansions and relations quickly. And the motivation here is from a common e-commerce use case. If I search for iPhone, typically I get back other things, iPhone cases and charges, which is fine, but they're mixed in, and often the relevance is not accurate. In fact, if you use TF-IDF on short descriptions, it's not going to work too well, and the reason is this. If I have 50 vacuum cleaner models in my index, what's the chances that the best vacuum cleaner will also have the most terms vacuum cleaner in it unless I've hacked it somehow? None, because they all have vacuum cleaner at least once, probably only once. So traditional relevance doesn't really help much, and we see this when we just put basically traditional relevance on e-commerce data, and we tend to solve it with signals, with boosting and stuff. But in this case, if I search for iPhone, I do want both, but I want to see iPhones first, and then I want to see the other stuff because retailers always want to upsell. So if you bought an iPhone, you might also be interested in buying a charger and a case for it, and here they are, right? But if I search for iPhone case, now I want precision. I don't want to see iPhones because obviously I already have one, or I wouldn't be looking for cases for it. So it's very annoying when I search for iPhone case and I see a bunch of iPhones and I have to find the cases. So this is a interesting case. And expansions or relations are a little thing I discovered that everybody actually knows about, but if you think about it for a minute, it's actually pretty interesting. So if I have these noun phrases that end in table, they're all tables. But if I have noun phrases that start with table, they tend to be table-related things. Like milk chocolate is chocolate, chocolate milk is milk, right? Because the second term is the subject noun in almost all cases in English. So you can apply a very simple logic to say that phrases that end in table are specific types. That's an ISA. And I want to make sure if I search for table, I get all these other things. But if I do search for coffee table, I only want to see coffee tables. Whereas relations are like is-like relationships. If I want to search for table, it's like the iPhone case. I want to also see the other things, but I don't want to see them at the top. So actually, the top one, expansions, I handled at index time by actually making multi-value fields. So a product is an end table, but it's also a table. And the relations is basically a query time thing where I said, okay, I'll just OR table with all those other things, but I'll boost table more. And I can do this, I can be more precise about this because I know what the things mean, whereas a TF-IDF will not only be looking at how often does the term or phrase occur. So it'll work, but the relevance won't actually be controllable. So here we're getting into the end of the talk, and basically I'm going to be out of time for questions, but I'll stand outside if anybody wants to answer. I assume this was going to happen. The problem with unstructured text is, yeah, it's unstructured, duh. But we typically don't facet on unstructured text because, even though we can, because you get all this facets on your UI, which are useless because they really all include all the noise words and everything. So we basically absolutely use this for UI drilling, so we basically don't do it. But since facets are context engines, I had a light bulb moment. So wait a minute, if I did fasten at them now at index time, so anybody can't see the gore, and use their stats to do some text analysis, I can actually show you that facets can detect keywords. And the reason this works is that keywords, if you think about it, are terms that occur in relatively few documents, but it's actually semantically reasonable that they do, because they tend to be important words in some subject areas, but not in others. In other words, their usage is highly contextual to a subject. So that's actually kind of an operational definition of what a keyword is, okay? If you see a particular word and it's a keyword, that means it's highly contextual. It's rare, but not too rare, but it tends to be common in documents that are about the subject that it's a keyword for. So because they occur together, they share the same context. Once again, facets are a great context mining tool. Hey, maybe we can do something. Well, here's the method to my madness. I tokenize the text with this auto-phrasing so I get things, not just terms, and synonyms. And did I miss a slide or something? No, I didn't. Anyway, auto-phrasing is basically a technique that you can knowledge that noun phrases are single things. I think I left out a slide, which is good because I don't have time for it. But an auto-filtering is something that uses that information. But they both are knowledge-based because an auto-phraser has a knowledge. You give it a lexicon, say these things like coffee table. That's one thing. It's not two things. It's not coffee and a table. It's a thing called a coffee table. So I used the auto-phrasing tokenizer to basically find these phrases and then basically put them into basically a text field with doc values. And the only reason I did that is because if you try to facet on text, they actually can only have 2 million separate values in a terms thing anyway, and it tends to blow up. Whereas if you tokenize them and then put them in a separate field and use doc values, then you can have as many as you like. And doc values are awesome. I could talk for a whole hour on that too, but I won't. So then I submit 2 queries, one with a term text field and the term as a positive, and the other with each text, the whole list, where I put a negative in front of which to Lucene means show me the documents that don't have that term. I usually use the proximity filtering to help out. And then I just calculate the simple ratio. The ratio on top is the facet counts for the positive query against the total counts for the positive query against over the negative part. And when I thought about this, I said, yeah, that should discriminate because only things that are in the same context will actually have a high ratio. And it should automatically filter out noise words, and it does a pretty good job of that, because noise words basically are going to have basically a ratio of 1 because they always occur in everything. There are a couple of them that are gnarly, so I did have to beef up the stop words list to make this work well. And then if you take the x log x of this, you get even better discrimination. The curve shoots up faster so you can threshold easier. So here's the answer that I got back, and I did this. Hello. Why is it doing that? There you go. So here is the first pass, and I picked the word authentication. And these are the other words that it found that are like authentication. And you can see it's doing pretty well. It's got firewall authorization, all security-related terms, but it's also got some other stuff in there that doesn't belong. So then I thought, oh, this is pretty good, but we can do better. So you note that authentication, authorization also has a cluster that goes the other way. So what I did is said, okay, take all these children of this guy and ask how many times these other things occur in their clusters. So what happens is related terms tend to vote for each other, whereas noise terms tend to not vote for each other. So then you take those counts in phase 2 and multiply them by stuff, and then you get this. Basically now you have a much cleaner list. It looks pretty good. There's still some things like bother, and I didn't do a good job on stemming in this particular example, so login, logins occurs. That'll help ACL, ACLs. But you can see these are pretty good vector of that keyword. So then what you do, okay, so now I've identified that authorization and authentication are keywords because they tend to occur in security-related documents and not elsewhere, so that's good. So I've got a set of keywords. I can now use those to facet and drill in and not the stop words. But then I did another thing which basically took those and used them as vectors in a classical clustering operation. So normally a clustering operation you use TF-IDF, which is everything in the document. In these vectors, I'm just using things I already know are keywords and basically computing a vector distance measure on those, and I'm using a standard clustering. And this is what I get out, and this is from some less than 1,000 documents on Lucidworks blog site, and the k-means will give you basically the statistics about cluster 98. It doesn't know what that means, but if a human looks at that and say, oh, those articles are all about Stump the Chump. And this is in honor of Chris Hostetter, who we're not doing Stump the Chump this year. But that was the first one I saw and said, oh, this actually works. Because you got Stump Price, Tough Question Judge, and you got people like Robert Muir in there, and Conference, and Lucene Revolution, and Chump, and Hostetter himself, Chris. So, and here's another one. You look at that one, you go, oh, okay, that one's about garbage collection. So if you label these clusters, and a human can actually eyeball these and say, okay, that's garbage collection, the other one's Stump the Chump, now you have categories, and then those are really good facets. So I'm over time, so I need to stop. For questions, 4 minutes over. Sorry. Next speaker. Thank you.